Good morning to everyone. Hope I'm clearly audible. If any of the participants can confirm.
All good.
Yes, ma'am, it's audible.
Yes, thank you so much. So we are here for the day 2 of the workshop, the SPSS workshop for research data analysis with the help of through SPSS, right? So yesterday's PPT has been shared on the WhatsApp group as well as. Good morning to everyone. Hope I'm clearly audible. So the PPT has been shared on the WhatsApp group as well as the Telegram group. I will be sharing the PPTs of day 1 and day 2, both with you along with the study material provided by Sir. Post this session in your registered email IDs. At the end of the session, we would be sharing an attendance cum feedback form with you all. So kindly register your attendance in that feedback form. And after that, your certificates will be provided to you within 15 days, right? So I am sure that each one of us will agree. We are all on the same page that yesterday's session was a very fruitful session. I have been getting very positive feedback about the session yesterday, and we are all looking forward to the day 2 of the workshop. So hopefully all of us are going to gain a lot from this from this workshop today as well. Somebody's asking for the Facebook link. It's on the YouTube, sir. And it must be sent in your mail. If you could please check the mail. So the live streaming is being done on the YouTube also. Okay, it's the feedback link. The feedback link I'll provide at the end of this session, sir. Yeah. And thank you so very much, all of you, for joining us for day 2. Over to you, sir. I think we are good to begin.
Okay, that's good to know. And also, very good morning to everyone, and also to Professor Shamla Hassan. And I hope you all had enough learning yesterday, and also you enjoyed the session. And today, I'll focus on hypothesis testing. If you feel that, okay, no, I was just presenting small stuff yesterday, and here comes the big stuff today. We are getting into the nitty-gritty of data analysis. Let me check. Okay, so I hope my screen is shared now, and you are able to see my screen.
Yes, sir, it's visible.
Perfect. All right, so let's begin. So what is our agenda for the day? And I'll just start with the need for statistics, because yesterday we talked about descriptive statistics and other stuff. But when it comes to statistics, we look more into the inferential statistics of it, right? So yesterday was more exploratory. You looked at the distribution of the data, you looked at the mean of the data. So mean, median, mode, and those three are called as measures of central tendency. If you look at deviance, standard deviation, variance, they are all called as measures of dispersion. So how far the data is spread from the mean. And today, so we are going to use the mean for many purposes, especially like we try to make some sort of inferences out of it. So we have data, and you'll see why we need statistics in that case, when I have enough data, and when you do not need statistics. So we'll look into those basic principles. And later on, I'll talk about the little, it's a very brief overview of research process. And in that, I'll tell you where the hypothesis testing will fit in. And then I'll talk about type of variables, because we talked in terms of levels of measurement yesterday. Both, as I told you, levels of measurement is important for hypothesis testing. I'll also explain that a bit later. And then I'll talk about the most prominent thing that may go wrong. So it's like called as type 1 and type 2 error. And also the problems with NHST. So in a sense, null hypothesis testing. So what is the problem with this NHST, right? And also I'll briefly show you the flowchart of hypothesis testing. So, okay, what are the it's kind of a guideline. So if you have a categorical data, if it's a dependent variable, and what kind of analysis that you should do. And later on, I'll focus on few hypothesis testing using SPSS. One is like chi-square test of association, and then paired and unpaired sample t-test, and ANOVA one-way, two-way, and regression. Okay, I hope 2 hours is a bit short for that, but still we'll try to cover all of this. And if you have any questions, feel free to stop by. And also, I think the chat box is also ready today. Hope you can feed in some answers. All right. Okay. Fine. So we'll start with this very basic question of why we need statistics. When we are collecting data, we cannot collect data from the entire population. In the sense, imagine you are trying to assess how shopping list is used by consumers, right? For that, you cannot go and access everybody and then collect data from them. Hence, what we normally do, we collect a sample, right? When you have a sample and you want to predict the characteristics of the population in the sample, then you need statistics. But when you have information about the entire population, and you don't have to worry much because you have the information already. You have the mean estimates and other stuff. They are pretty much enough. That's why the census data is presented as such, because it covers the entire population. But when a researcher collects data from a specific set of from a population, and then he not collects from the population, like he collects from a sample, then he has to prove that, okay, the sample that I collected is representative of the population. And to prove that, he needs statistics. This statistics works under the hood of probability, and we try to see how probable we are in collecting the true data that represents the entire population. Okay, so it's a standard research process. We have to do it, right? So let's look into the research process now. Okay, so the research process normally starts with a question. Right? So we try to address any question. So you may imagine that now there is a conflict between Ukraine and Russia, and we do not know what's going to happen economically, right? And there are certain news that is coming and saying that, okay, so the conflict between Russia and Ukraine can have an impact on Indian life, especially in terms of the economy, saying that the petrol prices will increase because the world market has increased their price from like $50 to $100 per barrel. Hence, we say that will definitely have an impact on the prices of fuel in India, right? So we are looking at the cause and effect relationship. There's a cause. The cause is your Ukraine and Russia conflict, and that leads to your fuel price increase in the global market, and then that's going to lead to further to the Indian market fuel price increase. And how we are able to do this, because we look into the previous theories that was postulated. We already have some sort of data. We observed it already, okay? And so we consult those theories and then look at it. And if we do not have enough evidence to prove that, okay, what we are trying to say, we will go and access certain samples and collect data from them. So we'll generate hypotheses. So we have some questions that are not addressed previously by any researchers. So now we frame these questions. So these small statements or questions are called as hypotheses. And for this hypothesis, we need some supporting evidence, right? If we do not have evidence to say how this fuel increase is going to happen, and nobody's going to believe you. For that, we'll collect data and then prove it. And when you have the data with you, you have to analyze and then say, okay, this has an impact on, imagine there is change in rainfall that will have an impact on crop growth. Right? And if you prove it, probably we'll normally go for a regression analysis and then prove, yes, if there is increase in rainfall, that will increase the crop growth. And then this result will be presented, and that will also further fuel and increase, changes your hypothesis if it's wrong, or then if it is not correct, and then we'll also consult the theory. Okay, and the ultimate goal is that the sample that they collected for proving this hypothesis should be a representative of, it should represent my population. If it is not representing my population, then I am wrong somewhere. Should look back into the data again and look back into my theory also, right? So we now know why statistics is required. So statistics is required only when you collect data, when you have a sample, and you infer or predict the characteristic of the sample and approximate that to the population. So whatever you observe in the sample, you say that, okay, it's the same for the entire population. And only then you need statistics. If not, you don't need statistics there. And now let's go to the next one. Okay, so there are three things that I'm planning to cover here in terms of theory, hypothesis, because we are trying to cover hypothesis testing today. So what is the difference between these three? So one is like theories. So theories are set of principles that basically explains the known findings. So there are certain things that people have already observed, and they have put across that information to you. Maybe if you're not aware, there is a theory called as Abraham Maslow's hierarchy of needs theory, right? And technically, if you look back into the theory, there is no statistical evidence saying that, okay, the theory is robust enough. But if you look at financial theories like econometric theories, Black Hole's formula, and I'm talking about Black-Scholes formula, and then any other hypothesis, they have like kind of a theory on rationality or something, and these have proper research evidence backed up with data, but not your Abraham's Maslow hierarchy theory. So you can still question these theories. So they are still established. They are they generalized certain phenomena into a theory, but it's not that they are all always right. You can still go and question the theory. So when you're trying to question, and the question itself is a hypothesis, right? Imagine I'm trying to put across an example here. Look into yourself in this situation. We know about COVID and how it had an impact on us, and we can have a very basic question like a researcher: and will people become more selfish, after COVID-19 because of the COVID? And we have experienced this for the last 3 years, roughly. And do you think people will become more selfish? No, they'll think only about themselves after COVID situation. So this is your very basic question. But you can also technically rephrase it in a sense, put it in the academic context and say, altruism tend to reduce in the presence of crisis situation. So crisis can represent any crisis situation, like maybe flood or other things. But what we say is that altruism will come down. But this is not the case, right? Because like when there is crisis, and people normally help other people. So if I want to prove that, okay, altruism is reducing, and as a researcher, I should collect evidence. I should collect data, and I cannot collect data from everybody. I can collect data only from few people. I collect the data from these few people and then prove, yes, what I'm trying to say, or the sample that I collected actually represents this entire population. And then when I actually prove altruism is actually reducing in the presence of crisis situation, which is going against the existing theory, and what I do here is called falsification. Right? I am disproving a theory or a hypothesis. Right? So main goal is that you establish certain statements, and those statements are the normal existing statements in the globe, and then you try to find evidences against it and then prove. Okay, so you normally think this is the case, but this is not the case, and as a researcher, I am proving that this does not normally happen. Okay, and next, so when you want to measure or when you want to prove certain things, and you are supposed to take care of certain aspects called as variable. Okay, it's a major thing. So hypothesis is there, and the hypothesis basically says altruism tend to reduce in the presence of crisis situation. So we can break this hypothesis into certain variables. What is called as independent variable. So independent variable is that it will not get affected by any means. Okay, so presence or absence. It should be or. So sorry for the mistake here. It's a typo. It's presence or absence of crisis situation. Okay. It's like existence, like COVID is there and it's not there. And the dependent variable is that dependent variable will be affected by this independent variable. So if there is a change in the independent variable, then we predict that, okay, so that'll be an impact on this dependent variable. Okay, so the dependent variable depends upon many other factors. So we call altruism as the dependent variable in this case. And then in regressions, we normally look at control variables. So we add many other variables that can also have an impact on this relationship. So independent variable is going to affect dependent variable, but the dependent variable can also change because of many other factors. If you do not account those variables into your model, and that will become a kind of a, it will not explain much. It's a kind of bad model. Right? So what we normally do as a researcher, we normally add these, look at to these control variables and measure them, and also add that into the model. Okay. So what do I mean by model? So model is something you normally know. For example, sorry for my bad handwriting, but right. So y equals a plus bx, right? So here y is your dependent variable and b is your independent variable, right? So we can say this is altruism, we are measuring through something, and this is your presence or absence of COVID situation. But what I say is that if I just only predict with this model, that's going to be bad because I'm missing out several other variables. But what I can do is like I can add any other control variables to the model, right? So something like your right? So I can add this control variable like economic capacity of people or mobility of people. What I'm trying to say here is that if people have more money and they can afford that money to many other people, they can show that, okay, they're altruistic, they are trying to help others. But imagine there is a person who is not having any money, but he's altruistic. He want to help other people, but he doesn't have the capacity. It doesn't have the money to help other people. And that will be, you are basically not accounting that. Hence, the economic capacity of people can explain certain portion of altruism, right? And then you can also have some sort of confounding variable. So media normally focus, like the news channels normally focus on certain people, when they are doing some philanthropic activity. They highlight on people who are, for example, say actors who are doing something good. But we only look at them. We don't look at the bottom level people, because there are people who could have cooked and gave food for their neighbors because there are some problems with their neighborhood, but they are not noticed. So the confounding variable is that how it is highlighted in the media. If the media says that nobody's helping each other, then we can say the altruism generally goes down. So we need to account these kind of confounding variables. So the confounding variables are other extraneous variables that can have an effect on the relationship that we are trying to predict here. Right? So by putting these things together as a formula, what I have done is like I have established a regression equation here. It's a simple multiple linear regression. So we have bx is one variable, that's the independent variable. Y is the dependent variable, and the control variables include many other variables. Hence, we formulated a multiple regression equation. Imagine if I remove these controls, I just only have this relationship like y equals a plus bx, and this is called a simple linear regression equation. Okay. However, I'll also explain these things in detail later. Let's move. Okay. Right. So now I'll check if you have any questions, and if not, then we can move further. Any questions until now? Okay, it looks like no questions. Then let's move ahead. Okay, so now what I will do is like I'll move on to the phase of hypothesis testing. So we established the basic framework that we need to understand hypothesis testing. Okay, and so it's a good time to shift there and learn how this hypothesis testing is actually done. Okay, so I told about hypothesis earlier, right? And still, we should also explain a bit more because there are many ways that this hypothesis can be set. And people could have learned this as like a one-tailed or two-tailed hypothesis, right? And this one-tailed and two-tailed hypothesis is a way that we establish your certain things, then you test on this hypothesis level, right? And always we try to establish a kind of two-tailed hypothesis, like bidirectional hypothesis. And if it is set, it is always good. But in some cases, it is good to have one-tailed hypothesis. Okay. Now I'm introducing some terms that might be a bit difficult to understand, right? So I'll try to split these things apart and then tell you what is one-tailed and two-tailed hypothesis. Okay. So for that, let's understand an example. Let's understand it from an example. The example that I'm going to give you is that if you're attending my statistics class and there is more chance that you will try to kill me because it is always confusing, right? So this is a hypothesis. So the hypothesis that I set is that it is a non-directional or two-tail hypothesis because there are chances that people are not going to kill me, but there are chances that people are going to kill me because they are really bored in the statistics class, right? And or we can have one directional hypothesis, like it goes into one direction, not in two directions. So I told about two directions now. So there are chances that they will kill me. There are chances that they will not kill me. But I'm talking in terms of one direction. Okay, certainly people are going to kill me. And that is called as one-tailed hypothesis. If there are two directions for this aspect, and that is called as two-tailed hypothesis. And why we should always look into this two-tailed hypothesis, because it has benefits. I'll talk about that in the upcoming slides. Okay. Now, when you set this two-directional hypothesis, or it's like a non-directional or two-tailed hypothesis, so what happens is that you have three possibilities in exploring. Right? So as I mentioned to you, people who attend statistics class wants to kill me more than others. It's a positive relationship, right? In a sense, positive relationship in the sense in terms of what we are trying to predict. And the people who attend statistics class wants to kill me less than others. So it's negative relationship, right? And then we can also say there's no difference between people who attend my statistics class and also who do not attend my statistics class. So the mean difference is 0. Okay. So now you can see how this number that we collect, right? Because we are collecting certain sort of evidence to prove that no, the hypothesis is right. If there is no difference, that's a normal course of behavior, right? So people are not going to try and kill me, and that the behavior is not going to vary from others and then people who are attending my statistics class. So that is the normal course. So this one, the final option is called as a null hypothesis. But if I say, no, as a researcher, what I should do is like I should also, right? If I want to prove that, okay, people who attend my statistics class, no, they have more chance that they are more prone to kill me, then I should prove these two, either a positive relationship or negative relationship. If I just establish one side hypothesis, like kind of one tail hypothesis, it becomes a tricky part. But it is better to always establish a two tail hypothesis because there can be either positive or negative relationship. So I can go in by that direction. Right? Hypothesis and what's a alternate hypothesis, and also what's the difference between two-tailed and one-tailed. Okay, so now I'm going to explain this one-tailed and two-tailed hypothesis in terms of numbers. Okay, so we explain now so far as a theory or as a kind of a proposition. But it is not always that we observe them as these qualitative stuff. We observe them as a quantitative information. Okay. So now imagine a situation. We expect the mean value to be 10. But when we measured and collected the data, we got a mean value of 12. So it's like 2 levels increase in the mean value. So should I reject null hypothesis and say, yeah, I think no, it is 2 level increase. So I should reject my null hypothesis and then accept the alternate hypothesis saying that, okay, there is an increase in something. But no, we cannot do that because you're going in one direction. So you're only looking this direction of like increase in relationship. So if you are just looking at that direction, and basically you are getting into the boundary of one-tail hypothesis, but there can also be other chances, right? So you can also get a different kind of proposition saying, okay, so from 10, it moved to -5 or -2 or like even just 5. So you're not, if you just frame one-tail hypothesis, you're trying to prove this on the one direction, which is very difficult all the time, and which is essential for some cases. For example, say, light bulb life, right? So every company promised that, okay, the washing machine will last for 8 years. And the light bulb will last for like, 1600 hours or something. So if you want to prove that, okay, I take a sample of bulbs, I take 100 bulbs and then allow it to burn. And if I collect the mean estimates, and if it is less than 1600 hours, right, on an average, then I can basically say, it's a one-tail hypothesis, right? So we want to have more than 1600 hours, or at least very close to this 1600 hours, but it did not happen. Hence, we are looking at this one-tail direction for certain scenarios. But when you try to measure behavior, or when you try to measure certain economic phenomena, you cannot only restrict yourself into the one-tailed aspect, because we do not know how it is going to behave. People can buy sustainable cars. People can also not buy sustainable cars. So hence, it is important that you go for a two-tail hypothesis. And technically, what happens is you split. There's the two-tail hypothesis has a split approach. Okay, and what is split here is the alpha value. Maybe this is not easy to understand by text, but maybe it is easier to understand by looking at the graph. Okay, we talked about the normal distribution curve yesterday, right? So here you can see this is the mean, and this is, you can see the mu naught is your null hypothesis. So what we say, this is a H naught is a null hypothesis. So we say both the means are same. It's not different. Huh? And the alternate hypothesis says that the observation that I made, right, or the samples that I collected has higher mean than the normal estimates. So, for example, say in this case, it is this 1600. Sorry, my bad. So this is just 1600 hours for mu naught. Okay, and what I'm trying to say is that probably we say no, the bulbs actually give more than 1600. It goes somewhere around 1800. So to prove this, what I do, I'll collect a lot of sample and then estimate these life of the light bulbs and then prove it. Okay, but what I'm doing here is like I'm just going to this boundary one direction. Hence, this is one tail hypothesis, and the alpha is your permitted error rate. Okay, how much error that you can have. Right, so error in measurement. And that can that is normally allowed like 5%. So you can have a 5% error rate. Okay, which means imagine you are trying to hit a target. So we talked about reliability and validity yesterday, right? You're trying to hit the target. So if you're a professional athlete, so you should hit the target properly at least around 95 times. So you can have error rate of 5%. So that can be done. That is allowed. So this is very plain example. No, this is not very suitable for a statistical approach, but I'm just telling you for a for easier understanding. And also another example would be, imagine that we are trying to develop a drug. In the drug that you developed is going to help you to fight against COVID. And when you administer the drug on 100 people, and the drug can fail on 5 people. But if it is going to fail more than 5 people, no, we have not developed a proper drug. Yeah. But in medical scenarios, so people, they do not actually have this error rate of 5%. They will normally have the error rate of like 1%. Why? Because no, they don't want many people to die, right? So they'll expect at least 99 people are saved by giving the medicine. Okay. So this 5% error rate is very common for psychology, right? Or sociological studies. You know, if you are even running field studies, you can also allow, some people allow the error rate up to 10%. You know, so the error rate varies from field to field. Okay, so now you understood why this alpha is given here. So every single aspect of like 5% is loaded here. So 5% translate to the normal normal number that we say in terms of the significance value or p-value. It's like 0.05. But this is not exactly applicable for the two-tail, right? So for the two-tail, what we do is like we split this 0.05 to 0.025 here. We test that one here, and then we need also put the other 0.25 here. Oh, sorry, previous slide. Okay. Clear? So now what happens is that you need to have more data to prove that when you split this error rate. And here it's probably easier to prove because you're going to one direction and it's easy to establish because you're only looking for the other's evidence. Okay. Hence, in general, if you look at any psychological studies or sociological studies, or beyond the kind of electronics and other stuff, people generally go for a two-tail hypothesis. Okay. Right. So, any questions here in terms of understanding one-tail or two-tail hypothesis? Okay. If it is there, then put it in the chat box, and then I'll look at it. So when you have this, establish this one-tail and two-tail hypothesis, and then you collect data, and then you're trying to prove your hypothesis, and you're trying to establish that to the people, scholarly people. You're trying to go and say, okay, no, I collected data and I got, I got positive results. And how can you prove that? No, there can also be error rates. And the errors are generally classified into two. So one is called as type 1 error and type 2 error. So the type 1 error is called as false positive. You go and test a man for pregnancy. Is it correct? Can we test a man for pregnancy? Absolutely not. No, that is not permitted. So which means if your test kit says, okay, you apply this test on a male and says, the test says, okay, that guy is pregnant, and the pregnancy kit that they used is completely flawed, right? So you cannot really do that. So the type 1 error is most vulnerable. So it's not vulnerable in the sense it's more, you should avoid that at any cost. And type 2 error is a false negative. We can clearly see this woman is pregnant, but the doctor says she is not pregnant. There's a bump in the, we can see that, okay, there's a baby inside, probably, it's not due to any other factors, but the doctor says, no, she's not pregnant. So that is called as false negative. But in any case, there's a good news, there's a baby and then she's going to deliver the baby. That's why this error rate, though it is also problematic, that it is kind of acceptable. But both are still problematic. If you put it on a scale, estimate which is really bad, then false positive is really bad compared to false negative. But in any case, as a researcher, you're not supposed to get these two errors. Oops, sorry. Sorry about that. Okay, so how can we understand type 1 and type 2 error? So I mentioned that type 1 error is the false positive and the type 2 error is false negative. So you have a steady finding, and that's a reality. So the study finding is your, I would say, sample you collect, right? And you are trying to approximate the population, yeah. And you're trying to see whether your sample exactly represents your, my bad, no, represents your population, right? If it is not happening, then we encountered certain error rates. Okay, so either false positive or false negative. Okay, so to understand it very brief, no, in a plain language, we also looked at the other examples like in terms of pregnancy. But here I want to explain one more thing that is called as no, power. Okay, so the alpha is normally set by the researchers as 5%, right? Okay, so we can allow only 5% error rate, but the beta statistician says we can allow an error rate of 20%. Okay, why? I told you, right? Because this one we are accepting at 5%, because this is more problematic, right? This is less problematic, so the statisticians normally agree to 20%. But in general, that should also be 5%, right? Since it is not more problematic, and that's why they set it as 20%. And so this is actually called as beta, and this is called as alpha, or the significance level or the p-value, right? So the power of your study, so how much you are able to tease out the effect, you should at least achieve through your study, you must at least achieve 80% power. And how can I understand the power? So it is 1 minus beta, it is equal to 0.80. Okay, and that you can see here. So it's you try to predict a phenomenon, and also you observe the same phenomenon in the population that represents the reality and the true positives here, but at least it must have 80% power, right? And this is not, no, people not worry about this. Why? Because it's not so interesting. No, if you predict something negative, it's also negative in the world, and nobody really cares about it, right? And so this matrix is also called as confusion matrix. If you are from the machine learning field or you're interested in that, we can relate with that. Okay, so confusion matrix. So it is very hard to write with the mouse. Maybe I should try and buy a pencil later on. Okay. So now do you have clear idea of or clear picture about, okay, so what is type 1 error, type 2 error, what is one tail to the hypothesis, and also why statistics is required? And if you have any questions, you can post it now. Can we use this beta or like power for something else? If anyone knows the answer, you can raise your hand or you can put that in the chat box. No? Okay. Okay, the power, the power can, if you know this power, you can estimate the sample sizes, right? So with the help of alpha, beta, people can estimate the required sample size for your study. The sample size, alpha, beta, they are all related to each other. That's why now, if you look at the Western world, initially they were not worried much about the sample size requirement and then power analysis. At the present moment, it is given more weightage. So one should pre-calculate how much sample is required to establish a power of 80%, and then collect that data, and then prove the phenomenon. Okay. All right. So I hope you got the crux of the topics that I shared now? And if not, feel free to ask. Oops. Okay. Now let's go to the flow chart. Okay. The flow chart will tell you if you have certain variables. Okay. We have independent variable, dependent variable. I mentioned to you about that, right? And the first level, this is from the book by Andy Field. Okay, Andy Field is a very good professor who explains statistics in a funny way. There's a book by him, Andy Field. It's called Discovering Statistics Using SPSS. And also, he also wrote another book called Discovering, kind of adaptation of the same book called Discovering Statistics Using R. And if you're interested in R, you can learn from that. If you're interested in SPSS, you can learn from Discovering Statistics using SPSS. And also, it's very cheap. It's not affordable, but still cheap in India. If you want to buy the same book here, it's going to cost me around 10,000 or 15,000. All right. So if you imagine sometimes you have the dependent variable just only one. So it is case of like y is equal to ax plus b. Yeah. So a plus bx. But sometimes what happens is that you can also have two or more dependent variables. Okay. Yes, someone raised the hand. Okay, so I hope there is no question. And if we have two or more dependent variable, then you can go for Manova, factorial Manova, and Manco. But we are not covering these things today, right? But we'll be covering a few elements from this category. So where we say, okay, there's only one dependent variable, but the dependent variable do also follow a continuous data. Okay, so I am not going to explain each and every piece of it, but you can see the nature of your the levels of measurement of your outcome variable and also your predictor variable will decide the test. Okay, let's go through one example and then understand. So imagine your DV, that's your dependent variable, is a continuous in nature. So it's a numerical data. It's like 20.5, 30.2, and XYZ like that, right? Then it has two or three predictors, in the sense it has 3 or 4 independent variables. It's here. And also, we say they are all continuous, in the sense they are measured in numerical data. It's like 20.5, 30, 40, 50, 16, something like that. So then you can see you can go for a multiple linear regression. And maybe if your sample size is not sufficient, if the assumptions are also not met, then you can go for a bootstrap regression. And sometimes it is also called as robust regression. Robust regression is applied when you have outliers and other things, because you have this linearity not met properly. Also, there are many other regressions that you can do. And also, if you go for one other example, like there is a continuous outcome and there is only one predictor variable, and that is categorical. And it is the categorical data that you collect, the normal data is more than 2, and then you can go for, and then it is all the same category, and it is called one-way repeated measures alone. So likewise, there are certain categories. So it's easy way to find the appropriate statistical test that you need to apply for your data. Yeah? For that, the important aspect is you should remember what I taught yesterday, the levels of measurement of your data, and whether it is coming from the same person or whether it's coming from a different person. Okay, here you can say the same is like the same person is responding again and again. Different means there is independence of observation. So there is no influence of one person on the other person's data. Okay. If you do not have any question, I can simply I'll just move to hands-on practice, and then I'll explain how certain tests are done in SPSS. Give me a second. just responding to a comment in the chat box. Okay. First, we will look at chi-square test of association. Okay. Let me try and pull out the data first. So what you can see here, you're seeing my screen that has data. What I have done is like I just collected data from a website which has different data sets for chi-square and other stuff, and it's a .sae file. So as I mentioned to you yesterday, if you just double click it, it will automatically open in SPSS. But for XLX and CSV files, you're supposed to go to SPSS first and then open the file. Okay, just waiting for SPSS to load. So once that is ready, then we can just run for chi-square analysis, right? I'll just write it here. So there are supposed to be two variables taken, for this test of association. There's also another thing called as test of independence, but I'm not covering that today. In test of association C, if there are two categorical data, and if those two categorical data are related, the categorical data is also your nominal data. Okay, so which means you have, imagine you have gender, and that is male, female, and you have education. It's like bachelor's, master's, and PhD. Okay, so there are you have two categorical data, and we want to see where there's relationship between gender and education. Okay, so maybe you can have certain hypothesis that females are more prominently studying PhD, or males are prominently they are studying PhD, and that can be a hypothesis, and then you can disprove the hypothesis or prove the hypothesis with your SPS, with your chi-square test. And importantly, the two variables that you have taken should not have the categorical data should not have only one group. It should have more than two or more than two groups. Okay, here we have two groups, and here we have three groups. Okay, so now let's get into IBM SPSS. So you can see there are two string data. Okay, and I'll just look at it here. And also there are values I mentioned here. Okay, we can look at the relationship between the gender. Okay, let's put it as cat 1. Okay, that is the categorical data 1, and also major cat _2. I'm just putting it for understanding so that I can easily pull out the data for analysis. Right. So what we are trying, the hypothesis that we set here is that, okay, there is a relationship between the gender and the majors that they choose for bachelor's, okay, or their primary major. Okay. As I told you, for this, the steps are just go to analyze, and then go to distributed statistics and cross steps. Okay. In cross tabs, you should say what should come in the rows and what should come in the columns. Okay. In the rows, I'm going to add the primary education. And then columns will be your gender. Okay. And also, please remember when you're trying to add information to rows and columns, the rows should have more category and the column should have less category. Or it can also go other way around, but it is easier to read through. Or sometimes it's also easier to read through. It depends upon people. Okay. Then you need to select statistics, and select chi-square, and then pi and Cramer V, because we are establishing having a nominal data, not ordinal data. And in order to find where there is a true association between these two variables, and pi and Cramer V statistics is helpful. Okay, and we also test the chi-square test of association, and then look at the strength of association with pi and Cramer's V. This one is a very basic statistical test, but if you want to know how much impact it has, then we go for pi and Cramer's V. Say continue. And also if you want chart, you can also select chart, select display clustered bar charts, then click OK. Now we will get the results. Okay. All right. So now you can see this is a case processing summary. We don't want that, so let me delete it. So this is first table that you're supposed to look at for interpretation. What we can see is like there's male and female, this one category, and females who study psychology is 54. Male who study psychology is 8. So there's a very big shift. The female favor psychology major, and males are kind of distributed. No, it's not that they are they just prefer one specific subject, but they are kind of spread out. They like economics, sociology, and anthropology, but not favoring psychology much. Yeah, it may not be the reality, but it's the data that's going to establish it. And then you can see the other basically has 4. Right? In chi-square, there's a rule that the cross tabulation between one variable with the other variable must have a value more than 5. You know, if the value is not more than 5, so which means the other has a value of 4 with female, and it's not appropriate for chi-square analysis. So what we normally do is, like, if we manually do it, we apply 8's correction and then do it. Okay, so here we are not doing that, but the system will automatically take care of those problems. Okay, and if you look at that results, you can see the chi-square value, so the p value is less than 0.05. So we talked about the error rate and stuff, right? And what we can see here is that it basically says there's a relationship between gender and then education. Okay, we can also see that in the bar chart. So because there is more females favoring psychology, and more males favoring economics compared to females. So what they say is that the difference between in terms of gender choosing education is a very prominent, and also it is significant. There's a strong relationship between your gender and the major that they are going to choose. Okay, so it's a very basic test to begin with, because we have 2 nominal data is the lowest form of data that we are taking, and then analyzing it. And now we can also go for the next one, right? So any questions here for chi-square with relate to chi-square? Okay, I'm just saving the output, closing it. Also close. Nope. Okay. Okay. So now let's go to unpaired or independent sample t-test. Okay. Has anyone applied the t-test in your setting, for your experiment or for your analysis, or maybe in the lab? Okay. Looks like no one has done it. And the t-test is applicable when you have only 2 groups. Okay, so there are 2 groups. Either they are paired or not paired. Okay, so we have 2 groups, and we want to measure if there is a difference between the mean of these 2 groups. Okay, and first I'll explain independent sample test. So that's group 1 and group 2, and they are measured separately, and there is no relationship between the group 1 and group 2. And they get the same kind of treatment or test, and we see if there is there's a difference between these groups. Okay, so let's put it as an example, then we can understand. We go to a class, right? And then split the class into two. And for this class, I'm going to give a placebo or a fake medicine, which will not boost any kind of immune system or something. It's a medicine that is given to them. And then later we ask, okay, how many hours can you listen to a lecture? Okay, that's group number one. Then group number two, they are also separate. No, they are on your right hand side. Now, for these people, we give a special medicine that we prepared, from the lab. And that for that group, and then we'll ask the same question, like how many, after consuming the medicine, and how many hours can you listen to the lecture? Okay. The expectation is that this group, the group number two, which is on your right, will be able to listen more compared to the placebo, right? Or sometimes also called as control group, right? So what we see is that we see two distinct groups, and they are getting the medicine, and we are measuring how much they can listen to the lecture. And in this case, we can only go for independent sample t-test. And what we see is independence of observation, those there is no dependency. And also the data that we collect, the number of hours that they can listen, should be normally distributed. Many people should say 1 hour, and that should be made to like 5 minutes or 10 minutes. So that should be a normal distribution of your data. Then that should be homogeneity of variance. So the variance of group number one, the spread of the data, group number one and group number two should be similar. It should not be different. However, there are also chances that group number one will be higher, and group number one is lower. So group number one has higher number of people, like 30 people are there. In the group number two, they are somewhere around only 15 people or something. So this group is better than we have a difference in the number of people. Okay, and in that case, what people say is like we should use Levine test statistics, or in SPSS output we should look at the equal variances not assumed. So the variance of the group are not same. Okay, I'll explain this a bit later. When I show you the data. Right? So this is a very basic setup. And in the setup, what we say is we have two groups, and these two groups are observed separately or independently, and we have some basic measure, and we want to see if the measure are different between these two groups. Okay. Let's analyze the data. Let's go for it. Let's see an example. Okay. So independent t-test. Okay, so we are going to take two things. One is maybe in the class, maybe you can identify which one is suitable, which variables are suitable out of these 8 variables. Which 2 variables we can take and then use for analysis. Maybe I can also show you the data view, right? So you have ID. ID is a respondent ID, so we don't want that. But there is sex, male or female, and reversed. So reversed or not. And also you have the depression, anxiety, and other measures. Okay, so we can look at that here. So anxiety, depression test, compulsive behavior test, like you have tendency to buy more, and antisocial behavior test. So they are not social with people, so they cannot mingle with people. And which of the 2 variables can we take and then measure? Okay, So there are two qualifiers. So we can take sex and then compare, or gender and compare these continuous variable like anxiety, antisocial stuff. You can also take divorced or not, and then their depression and then their antisocial aspects. Okay. So let's analyze it. Let's go to analyze. And as I told you, right, so it's easy to find in SPSS because we are trying to compare means between the two groups. And also you can see the name of the function is also same. We are trying to compare means, click compare means, and then we click independent sample t-test. Okay. And you can add the test variable should be continuous. Okay, that's a very basic understanding, right? There's one grouping variable. The grouping variable is divorced or not. It's a nominal data. And you can add all these continuous variables. Right? And also somebody asked whether if I misclassify the data in SPSS, will that produce result? And you can see the depression test score is kind of misclassified. It is considered as a normal data, but it's actually a continuous data or a numerical data. Hence, what I will do, I'll also add that one to see whether it produces results appropriately. Yeah? So then the question from yesterday will be sorted. Now I can click divorced. That is important because I need to define the group. And if I click define group, and by default, there are some values, 1, 2. Okay. But I should exercise caution here. If I do not exactly classify, like how the data is represented, like if it is zeros and ones, I should give it as zeros and ones. If it is 1 and 2 there, I should also give it as 1 and 2 here. And if I misclassify it, and SPSS will throw an error. I'll show it now. Okay, I'm going to say okay. And options, let's see. Okay, so there is nothing that you can do much, and say okay. Right. So you can see you don't get any results because we misdefined the group. It is not clearly defined in the grouping. So let's perform the test again. But if you want to correct your mistake, just go to data view and see. So divorced is actually given as zeros and ones. So there is one group, it has 0 value, the other one has 1 value of 1. Now let's go to independent sample t-test again, run it. And here just click define groups. Don't go to the default, say group 1 is 0 and group 2 is 1. Then click continue and then press OK. Now you get beautiful results. Okay. And now what we have done is like we took one group, divorced or not, and then we tested, we ran actually 4 t-tests here. So score on anxiety and then the influence of group. Now whether difference, if there is there any difference in the anxiety scores of people who are divorced or not? That was tested here. And the significance value is more than 0.05, which means there's no difference in the anxiety test score that they get, whether they are divorced or not. So there's no difference there. But the depression test, yes, there are people kind of depressed more if they are divorced or not. So there's a strong, there's a significant relationship between divorce status and then the depression score. Okay, and maybe you can, if you want to know more, who is more depressed, then you should look into the mean values here. And what we can clearly see is that the divorced people are more depressed because the mean value is 17.50. And people who are not divorced, and they got a score of only 15.67. In general, people are depressed, but people when they are divorced, and they are more depressed. Okay. And similarly, we don't see any problem in the compulsive behavior. And also we don't see we see a significant relationship here in the antisocial behavior test. Okay. People who are divorced are not social. People who are not divorced are kind of very social. Yes, Manjula.
Hello, sir. Actually, the screen is not visible. I mean, the slides are not visible.
Ah, really?
Yes. It is visible.
It is visible. Ma'am, can you please check your internet connection once, or you can refresh and join back?
Yeah, because because of the internet connection itself, I'm able to talk to him. So I don't think there's a problem with the internet.
Okay.
Okay. Anyway, I'll log in again. Yeah, thank
Yes,
you.
yes. You can refresh once and join back.
Yeah, right. Yeah, thank you.
All right.
All right. So because I'm sharing the entire screen, so whatever I'm doing on the screen should be visible to you all. All right.
It is, sir. It is visible.
Perfect. Right. So we also looked at one important aspect, though, if the variances are not same. So if the variances are different between two groups, then we need to look at a different level. Okay. And so if both the groups share the same variance, I will look into this data here, yeah, first level. If the group has different variances, if it comes from a different levels of variance, and then I will look at the bottom. Okay, right. So this is how you should read between the lines of the output and then interpret it. Okay. First, what you are supposed to do, you don't have to really look into the group statistics. Just come down and then see your significance level. And if the significance level is less than 0.05, then you can then go and compare the means. Then find who is actually doing worse or best. Right? But now that will be another question: how can you actually say whether the variances are same or not? For that, we need to go back to the previous lecture where I talked about normality. To run the normality test between these two groups, and then find if there is normality, then go ahead. If the variance are same, just go ahead. Or it's like, don't worry about it. If it is different, then interpret from the bottom. If it is same, then interpret from the top row. Okay. All right. So right now we cover two tests. So one is chi-square test, which has two normal data, and then we moved on to this t-test, where the dependent variable is a continuous number, and your independent variable is your nominal data, right? And there is independence between these observations of the two groups. Yes, Krishna Gupta.
Good afternoon, sir. Sir, can you please explain this equal variances assumed and not assumed again?
Yeah. See, we talked about measures of dispersion yesterday. So there's a spread of data. So there should be normal distribution of your data, right? So that is what we explain as there's mean, and not everybody will go near to the mean value. So some observations will be away from the mean. And if that is away from the mean, it can also be measured. It's called as deviance, and deviance can also be represented as standard deviation, and then also taken into the aspects of variance. Okay, so the variance tells you the measures of spread. So what we expect is that here, in this case, we expect the spread of group 1 and the spread of group 2 to be same. Okay, if it is not same, if spread are not same, probably some is skewed like this, the other one is skewed like this. If spreads are different, then we should go for equal variances not assumed, right? Maybe sometimes it can also be like this. No, the group 1 is like this and the group 2 is like this. So this group 2 and group 1 is like this. Then the equal variances cannot be assumed, and you go and read the bottom row of your output. If you observe the group and group 2 are like this, they are same. So then what you can do is, like, you can basically go for your first row and then say, okay, equal variance assumed, and then test it. And also that, I think that's also a very good question, right? So you can also apply a Levene's test on your data and see whether they are equally, there's equal variance or not. Okay, I think that will come in the next slide, the next level of analysis, and I can show that again. Okay, let me see if there is an option here. It's not here, but you can do that with the dependent sample details. Okay. Hope I answered your question, Krishna.
Thank you, sir.
Okay, perfect. Now let's go to the next test. Is paired sample t-test or dependent sample t-test. Okay, so initially we split the class into two, right? And then we said we are going to give you a dummy medicine, and then we are going to give you the actual medicine. And then we tested how many hours they can listen. Now what we are going to do, we are going to put them together. So it's only one group, and then there's a before and after. Now we always see this in Instagram, right? So before dieting and after dieting, there's a monumental change in your body. Yes. So if you want to test that statistically, then you go for paired sample t-test, because you observe the same from the same person, observe some phenomenon from the same person. So what we do, we take a measure before they are dieting, and then we take the measure after they are dieting. And if you want to prove whether there's a statistically significant difference in the weights, then we will prove, okay, the dieting actually works. Imagine that everybody is going on a keto diet or something, and you want to say, the keto diet works. So what you do, before keto dieting, you measure the weight of people, and after keto dieting, you'll measure the weight of people. You'll not do for one person, right? So you'll measure for many people like that. Then this data will be assessed for put into test, and then see whether keto diet works or not. So again, the assumptions are like just independence of observation, and then you have normality. Okay, and the test is also quite similar. Go to the same steps are same in terms of going through SPSS. Only thing is that you need to select dependent sample t-test. Okay, so same person measured in two instances. So it's like before, right? And then after, right? Or a student before training or after training. So if you want to look at this aspect, and what you do is like a dependent sample t-test. I'll just load the data and show you how it can be done in SPSS. Give me a second. Yeah. Because it's also called as paired sample t-test. And let's go here. So that is exam 1, exam 2, exam 3. Okay. And I cannot simultaneously compare these 3 exams and say, if there is any difference when it comes to t-test, because we can only compare 2 groups. But there's an option within SPSS that you can do it simultaneously. You compare exam 1 to exam 2, and exam 1 to exam 3, and exam 2 to exam 3. That's possible. Okay. Same approach. Go to analyze again. Then compare means in paired sample t-test. Okay, or also called as dependent sample t-test. Now you can see the window itself is a bit different, right? So you just click exam version 1 and go for it, and then compare that with exam version 2. So this is the first pair that I'm comparing. But I told you I'm not just interested in one pair. I'm also going to add other 2 pairs. For example, I'm comparing exam 2 with exam 3, and then exam 3 with exam 1. Okay, so we are estimating 3 pairs. So if you want to put it in the hypothetical way, we are actually in terms of hypothesis, in terms of testing, we are running 3 paired sample t-test. Go to options, and you don't have to do much. Because we are looking at the confidence interval of like 95%, and we are not worried about the effect sizes here, because I'm not explaining what is effect size and other stuff. Just go for it. Okay, so the output is ready. Let's have a look into that. So what you can see here is like it's a mean, right? As I told you, it's not important immediately. but you can go and look into this box, right? There's a paired sample correlation and also the paired sample test. So there's a correlation between these two measures, exam 1 and exam 2, and you test whether the correlation is significant or not. But if you want to look into the t-test results, then you come here to the paired sample test. So the first pair is exam 1 compared with exam 2. So we want to see whether there is a difference between the performance in exam 1 and exam 2. So students are taking exams. So they took exam 1 and then they are going for the exam 2. And if there is any difference in the scores that they got, whether they improved from exam 1 to exam 2. If you look at, go down and try for the significance level, we are looking at two-sided, because exam performance can get worse or can also improve. Some people get worse, some people get improved. So here the p-value is 0.33, which means there is no difference between exam 1 and exam 2. The scores are quite same, right? And also you can see the mean will always get closer to 0. If it is very closer to 0, and you can say, just by looking at that, you can basically say, there is some problem with your the null hypothesis will be accepted, not the alternative. Yeah. But when you compare exam 2 versus exam 3, people have improved. Right? So from 2 to 3, and there is an improvement. Right? Maybe people performed really well in exam 2, but not. For that, I'll normally go here. So let's try and find. So in exam 2, people scored 22.58. In exam 3, they got 20.58. So that's the difference. So 22.58 minus 20.58 is 2 here. It basically says that there is significant difference. So which means people have scored more in exam 2 than in exam 3. So it went up and then went down. So exam 1 was lower, then exam 2 was a bit higher. In exam 2, they came down again. So then also you can compare exam 3 versus 1. It's also significant, but the performance is poor. In exam 3, they are performing really well. They're not performing well, right? So there's also the effect size statistics. So the effect size will tell you how much it is applicable or practically valuable. But since we are not really talking on cogents T and effect sizes, I'm not going to cover that today. But because it's a separate session by itself, it covers all these power analysis and also the effect sizes, null hypothesis testing. You have to tease more information out of it. Hence, I'm not going to cover that. Right. So this is how you run independent sample t-test and also a dependent sample t-test. And any questions here? But I will also emphasize one more thing when it comes to dependent sample t-test, because you have ID here, right? You have exam 1, exam 2, exam 3. The data loaded, the data view is different. It is not exam 1, exam 2, exam 3 here, and then the scores, and then ID. So data has to be properly entered for a dependent sample t-test. And if you look at maybe I think I have the other one as well. Just give me a second. Yeah, for this one you can see it is reversed, and then we compare these two. Scores are from here. So the way that you enter the data will also have an impact on your analysis. So hence ensure that you appropriately enter data for the analysis purpose. Okay, but you can look. I will send these SAE files to. I think I have already sent. She can send it to you later. You can explore that one. Okay, so I think we are done with t-test now. Let's move on to ANOVA. Okay, so first level we compare two different normal data. We want to see the association that is called Chisquare. The next level, we looked at one variable is continuous, the other variable is nominal. One variable is interval, and then the other one is nominal. And there we apply t-test. Right? If it is coming from the same person, dependent sample t-test. If it is not, if it is from a different person, independent sample t-test. But what happens if you have more than 2 groups, right? So t-test is applicable for 2 groups. So if you have more than 2 groups, then t-test is not the right one. Okay. So what we do, we will go for one-way ANOVA. So the case here is imagine education. Okay, I'll put it as EDU. We have bachelor's. Okay, and then master's and a PhD. Okay, and then you measure the salary that they get. Right. So what's the average salary the bachelors get? And what's the average salary the master's students get? And what's the average salary the PhD students get? And also, and what we see, if you want to compare the means of more than 2 groups, we go for one-way ANOVA. And what it typically does is that it looks at variances within the group and the sum of square difference between the group, and then assess it. Since I'm not really much, interested in looking at the math part of it, I'll just tell you the very overview of it, and then share how we can interpret results from SPSS output. And one-way ANOVA is a basic form of your regression. Okay, you can also write, instead of doing one-way ANOVA, sometimes you can also go for regression. That is also possible, right? Because it is quite similar, right? So you have the salary. You can you have the salary, and that's the DV, right? And you can predict that with your education. Yeah. Okay. So if you predict salary with education, now it becomes a linear regression, right? So that's why you can see there is a change in the way that you can also select options within your SPSS window. Initially, you select the generalized linear model, and then you need to select univariate. Okay. Then you add what should be the DB, what should the independent variable, and then you can select options and dictate what you want to exactly produce. The assumption for this particular test is that independence observation, which is already known to you, and normality, again known to you. So there is normal distribution of the data, right? And especially the salary data. So if it is skewed, then you need to run other test. And then homogeneity of variances, which means not both the groups, like between these 3 groups, should have homogeneity of variances, right? So which means they should come from equal variances, right? So if you want to put it in this kind of scatter, on a scatter plot or something, or on a XY graph. So this is, for example, say bachelor's. Pretty bad at doing that with mouse. Sorry for that. Masters, and then a PhD. Okay. So what we expect is that the bachelor's salary, average salary of the bachelor's will be lower, but can also go higher. So what happens is that there will be a normal distribution like this, right? Okay, so it's typically not a great normal distribution, but assume that it's going to be like this, right? Then there's a master's student. Master's student will also get even more higher salary, but the assumption is that the variance should also be the same, right? Like this. So the distribution in the variance, right? So it's the spread should look similar. That's the idea here. Then here also the PhD will get a bit even more higher. I'm not sure how this actually works in India or in other countries as well, right? We assume that as you educate more, your salary get more. The average salary get more. So if you connect these dots, it will be like this. So as you educate more, and your salary will get higher. However, the distribution of this salary is equal. There is the equal amount of variance should be there. So if it is not there, then it is not a homogeneity of variances. Okay, this you can find from certain thing in SPS. The book that I mentioned, right? Discovering statistics using SPSS. He clearly mentions in a chapter about this. Okay, so let's stop looking at a lot of statistical stuff. Let's get into action. Let's do our analysis in SPSS. Okay, so one-way ANOVA. And double click the okay. So you can also see the entry, data entry. Yeah, right. The fertilizer is 1, 2, and 3. Okay, the 3 categories. As I told you, it should be more. If you have more than 2 categories, and you are supposed to go for ANOVA test, and then wait. So what we have done here is like, so in one plot of the agriculture field, nothing is added. Okay, so let's have a look into the labels. Okay, none was added. So it's a very plain field, it's kind of organic cultivation, right? So you put in the seed and see the weight of the seed. Then you go for an organic, then apply organic fertilizers and then see what's the difference. Then you apply chemical fertilizers and see what's the difference. Okay. And if you want to compare which one is better, what's the better method, then you apply one-way ANOVA. So generalized linear model, sorry, not generalized, general linear model, and then see univariate. Okay, DV is your continuous variable. Okay, it's a continuous data, it's your DV. Put that one in. Fertilizer used is your fixed factor, and also there are random factors, covariates, and other things. We are not also covering those stuff. But if two variables go together, they also co-vary, and that is called as covariates. Okay, and covariates can explain a bit of variance. It can also be sometimes annoying for your results, so that's why the covariates are here. Yeah, and because it can either increase or decrease your strength of the relationship. So that's why the columns are given here. If you want to use it, you can use it. If we have some covariates, add that one in. If not, leave it. Okay. And then random factors are other things. I'm not also worried much about that now. Let's look at the model. So we are just going for a full factorial model. So we're not worried about other things here. And then you can click plots. And if you want plot for something, and you can also do plots. I think by default you'll get a plot, and I'm also not worried about that. Let's see here, you can also run homogeneity test. So we said there should be homogeneity variances. That is like there should be equal variance between the groups. And initially I told if you want to test homogeneity variances, you can do it in one analysis. So here, especially with one-way ANOVA, you can do that. Then you can also get some descriptive statistics and effect sizes if you want. Then just go for continue and say okay. You get the results here. Okay. So this is the number of participant per group, or number of response per group. So none has 30, biological has 30, and chemical has 30. So which means there's the equal number of people in each group. So it's a very good sign. And equal number of plots in one group. And then we see what we have to see. If you want to immediately look at the results, go here. So this is between subject effects, and then you look into significance of the model. Okay. And here, what we can see, if you the p-value is less than 0.05, so which means that is a difference between there is some effect of some of the things that happened, right? So maybe if you look at the distributive statistics, you will get an idea. So the weight of the parsley is higher when you add chemical fertilizer. It is 56.97, and for the biological group, it is like 53. So if you just leave the field as it is without anything, and the weight is lesser. But if you increase, if you use biological fertilizers, and it is going to be 53.63 grams or something, and the chemical fertilizer is like 56.9. So which means chemical fertilizers have an impact on the growth of the crop. Okay, and this is given here. Let me see. We can also run something else. Let's try to put some plots. Okay, so I'm not getting any plot here, but you can also plot it. You can also go to graph and then build a chart and see what's the difference. Let's go for bar chart. Okay, then the fertilizers should go in the x-axis and the weight should go in the y-axis. Then click OK. Okay, so that's the difference, right? But what basically the test says that even though the differences are small, but that's a significant difference between the group. Okay, and let me see if we also, sorry, remember that, can run some post-hoc test. So now, why we ran post-hoc? Because now we know that there is difference between the groups, but we do not know which, there are 3 groups, right? Which group is having difference? One can be, one can be, cannot be different with others, but the other one can be. Group 1 is different than group 2, but not group 1 and group 3. So how can we really find it? So we can find it using the Taki test. Yeah. Okay. Taki test is used when you assume there is equal variances. Since we do not know whether it is there, and for that I told you that we should look into the results here. Right? So for any normality test, the significance value should be more than 0.05. Here it says it is 0.596, which means it is more than 0.05, which means there is homogeneity of variances. Okay, so it kind of represents this one. The equal amount of variances are assumed. Okay. All right. So let's go for that again. The post-hoc I'll explain. Again, this post-hoc. Since we have equal variances assumed, then we can select t-test. Okay. And if not, you can see there are other tests here. If the equal variances are not assumed, so which means you give me a second. Which means you get significance value here for the living test, right? Then you select some of the tests here. But most predominantly, mostly people will go for Games-Howell test. Okay, then click continue, then say OK. Now you can see the the post-hoc test results are here. And the post-hoc test results say none is compared with biological, and there is no difference between none and biological. Why? Because the significance value is more than 0.05. However, if you leave the plot just like that and then but you add chemicals, there is a difference. It's none versus chemical is significant. And that is 0.21. Okay, it is always I minus j, which means none minus chemical. But if you want to know how chemical has really worked, then you need to look into this. So chemical minus none, so which means when you apply chemical fertilizers, there is 5 grams increase in the weight. So it is significant as well. Right? So this is how you can tease apart information. We initially know the model is significant, right? Because the significance value is less than 0.05. But we do not know which one has had an impact on the DV, right? On the weight. So whether none is better than biological or whether none is better than chemical, or biological and chemical are better. Right? We were not knowing that. For that, we looked into the post-hoc test, and it proves that chemical fertilizer is better than leaving the land with nothing. But chemical fertilizer is not great than the organic fertilizers. That is what is proven here, right? Because it is not significant. So, but leaving just with biological fertilizer is also not great because it is not better than none. So we can with this result, we can say that adding chemical fertilizers increases the weight of parsley. Okay. All right. Any questions here so far? Because we covered one-way ANOVA, then I'll go for two-way ANOVA later on. Okay. There is a question in the chat box, which was asked by Keki Kulkarni. If numerical variable do not follow normal distribution, then is it possible to convert it into normality? Yes, you can take a log of the data, take log of of the normal of the numerical data, then you will get normal distribution. So that comes under data transformation. Okay, it's not a big topic, but can be covered in a lecture, like in 15-20 minutes. But that can be done, so that you achieve normality. Okay, and also you should not worry much about the numerical variable. If you're trying to fit a regression model, you're supposed to worry about the normality of the error, but not the variable itself. Hence, I'll not worry much there. Okay, I'll get into that area in 10-15 minutes. Okay, so now I hope we have we learned what is one-way ANOVA. Now let's go for two-way ANOVA. Okay, in the two-way ANOVA, now what happens is that we are going to have two normal data, and one interval data or ratio data. Let's put it as 1. Okay, so which means you look at gender, okay, and then education, and then salary. Okay, so these two normal data, they are all independent variables, and then this is the dependent variable. Okay, and gender is going to be male, female, and education, as I mentioned to you earlier, is like bachelor's, master's. I'll put it as P here for PhD, and salary is like 1,000, 2,000, and something like that. Okay, so how we will model this? So we'll model this like this. So sorry about that. So salary predicted by your gender plus education. Okay, that's how we'll predict it. And as whatever I mentioned for whatever condition that I mentioned, assumption that I mentioned for one-way ANOVA is also applicable here. Okay, so independence observation, normality of the data, and homogeneity of variances. Okay. Now let's go to analysis here. Let's any questions? Any questions before we run two-way ANOVA? Okay, so if not, let's go ahead. I think I made a little mistake. You can also do one-way ANOVA from here, from compare means. Okay, so but also I did it with univariate. Okay, the two-way ANOVA can normally be run here. So for one-way ANOVA, there is an option already here. You can do that. Okay, I think when you do one-way ANOVA from here, and it gives you an option to plot it directly. And that was my mistake. Maybe I need to look into my instructions, which was not correct. Okay, let's do that here again. So I'm just running one-way ANOVA because I made a mistake there, but the results are same. The results are not going to vary. So this is going to be weight, and then followed by factor. Then postdoc is select Turkey, because we already know that it has. You can also select what you want, and then you can also select means plot. Then press continue, and then say OK. The sides got mismatched, so that's why I could not really show it to you. See, you get the kind of same results. Okay, it's not going to be different, and the results are same. But you can run either through the univariate option, but also you can also use the compare means and then take one-way ANOVA. So both are same. The results will also not vary, but it's easier when you run through going to compare means and then pick one-way ANOVA, because you get the graph as well additionally. Now let's perform two-way ANOVA. Okay, so now it goes back to the general linear model and then univariate. Okay, so you can see there's one dV. The dV is supposed to be your continuous variable. So I have marked it here as dV for understanding. So maybe when you are running, then it will be easier for you as well. And then the fixed factors, gender, and then the medicine administered. Okay. So what we are trying to study here, the hypothesis that no, there is no difference in the depression score of people based on gender and then medicine that they were taking. Okay, that's a null hypothesis. But if you take the alternate hypothesis, it will say no, there is difference in the way that they gender and then the medicine that they take has an impact on the depression score. Okay, and we can do multiple things, as I told you. You can go for postdoc for medicine or for gender, but in general, no, you can do postdoc for the higher categorical group. So if if the normal data has more than 3-4 categories, then use postdoc there, rather than just looking for gender. Even if you use gender, that is also okay. But however, you can easily tease out information by just looking at the mean differences, but looking at the descriptive statistics table. Press continue, and then okay, and can also there's also intercept is also already included, hence I'm not worried much. So these are the factors, correct? And then go to options, and if you want anything like homogeneity test, try and do that, right? Descriptive statistics, click that one, then continue, right? And then just press OK. Now we'll get the results. Let's look at it here. Okay, so we got the results for this two-way ANOVA, right? There are two normal data. So one is gender, the other one is medicine administered. Okay, so they administered 4 medicines. So it's like a control group, they never got any medicine. There's a placebo group, they got something, as I told you, right? So there's a dummy pill they got. The other ones got homeopathic treatment. The other one got like a chemical, pharmaceutical, like allopathic treatment, right? And gender-wise, there are 46 males and then 54 females. And let's not worry about this table, as I told you, right? So let's look at the model and other things. Then come back to the descriptive statistics. By just looking into the Levine test of equality, we can see it is more than 0.05, which means there is homogeneity of variances. Equal variances are assumed, hence we don't have to worry much. Okay, and also you can see the model is given here. So there is intercept, this constant. So there's a mean value of the depression, and you have gender predicting depression and medicine predicting depression, and then looking into the interaction, how these two together predicts depression. And we are going to look at that here. Previously, when I was working with SPSS 17 or something, you need to define the interaction. So you need to tell which variable will interact. But now the interaction is kind of automatically incorporated as a tool. Hence, that's why I was searching for the tool, but it was not there. It's automatically added. Include intercept in the model. If you just uncheck it, intercepts will not come. If you want to check it, if you check it, and then you will get the intercepts. Okay. And I think if you build terms, you can add those interaction here, and then you put that one in. And this is also another way to add interaction term. So what do I mean by interaction? Interaction is the joint effect of both gender and then the medicine. Okay, so that is also estimated here because it is by default it is adding this interaction term. Okay, now let's interpret the data. Now interpret the results. Intercept is a constant. Okay, so it's don't worry about we don't normally worry about the intercept. Look at the gender. So gender is significantly related to the DV, which means the depression score vary based on gender, and also it vary based on the medicine that is administered and the interaction. So jointly, gender and then medicine together also has an impact on the depression score. Okay, so now let's go for post-hoc test. We should know which medicine is performing better on depression reduction, and you can see none versus placebo. So even just taking the placebo, when people, it is like, okay, so when you go to hospitals and doctor know that you are not doctor know that you are feeling good, right? But what you do when you go to the doctor, you normally expect the doctor should do something for you. And what the doctor will do is like they'll give you a dummy medicine, like he will administer vitamin B or something, and then say, okay, no, you are all good. And that is called as placebo effect. Okay, what we can see is that giving nothing doesn't do much, but by giving placebo, there's a significant difference in the depression score. Okay, and then none with homeopathic. So if people get treatment for depression, they generally feel that okay, they are getting better. And however, for some reasons like the chemical drugs have a strong impact on people's depression, so it can reduce it. But for that, if you should not look into this table, and it is better to look into this table, right? The pharmaceutical compared with none, or pharmaceutical minus none, it has a least depression rate. It means allopathic drug is able to reduce depression at large, and compared to placebo and then homeopathy. Okay, so only thing that is worrying is that there is no effect of there's no difference between homeopathic medicine and placebo. Okay, right. So any questions here in terms of two-way ANOVA? So we and then if you plot the results, and you'll be able to really understand how these things work together. But I think we may not have enough time for that. But you can just go to chart builder and then select appropriate charts and then build it. Okay, if there are no questions, then I'll go ahead with the next and the last test for the day. It's regression. And also it is not really easy to explain regression in 10 minutes or like in 15 minutes time, but I will try to do my best. Okay, so the assumption, the regression is already explained through ANOVA, because there are a different format of regression. And in general, the regression equation is you have y predicted by x, right? This is how we learned from the school. Somebody could have also learned, y is equal to m plus b x or something. It's different. But the y is the dv, in a is the constant, and or intercept, and or the mean of y. Okay, so if I want to put it like, it should be mu of y, and b is the beta coefficient. So it says how much impact x have on y. So if I increase x by 1 time, and what will be the result of y? So yx is the independent variable. Okay. So the assumptions is that each levels of x are independently observed, because it's not from the same person again. And then you can also look at normality. The normality is for the errors. So it's the important point here. Right? It's not for the data. No, you are not worried about the variables that you're taking. So you're actually worried about the error that the model is going to throw out, and the error should be normally distributed, which you normally do not see much, right? So we'll normally calculate the deviance And then the deviance should be normally distributed. And also there should be linearity between predictor and dependent variables. So which means if X is here, right, there are different levels of X, there are different levels of Y. Sorry about that. Okay. So in X increases, sorry about that also, sorry, and X increases and Y also increases. That's one type of linearity. And there can also be other way of linearity in terms of X increases and Y decreases. Okay. And what this will say, this is no linearity at all. Okay, so there's no effect of X on Y. And there can also be other things like this, because not all the time you'll have the exact line of connect. You normally have a spread like this. Okay, and this is a scatter plot. No, we normally, when you want to look into the relationship between variables, especially numerical variables, we go for a scatter plot. So the aim of regression is to connect all these lines and produce a line of best fit. The line of best fit is explained by this. So also the aim of the line of best fit is to reduce the distance between these dots and then the line of best fit. Okay. So for example, if I take another line like this, okay. So imagine that we have dots like this here, 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 and okay. And so these are the data points that we have. So one cannot draw a line of fit like this because it is not connecting the data points. Okay, so that is definitely not the line of best. So the regression equation will try to minimize the errors, and that's the whole purpose of regression. So what do I mean by error? So this is line of best fit and the deviance between the line of best fit and each data points. Right? There are many things, but I'm not covering all of them today. But if you want to explain only regression, it will take another 1 hour or more. Since one amount of time, I'm just avoiding it. But we have the difference between this data point and the line is there. And also that will be another line that's called the mean of Y. And the difference between the data points and the mean of Y is also another kind of error. There are some total sum of squared errors and sum of squared errors. That is this, and sorry, that is this, and there will be sum of squared residual. These two form this total. So there's residual error. There is also error. No. But I'm not explaining what is residual, what is error right now. But let's just to move ahead and then try to understand the very basics of regression. And maybe in some other occasion, I'll explain more on regression. And again, there should be homoscedasticity of variance, but it's also for the errors, not for the actual data. Okay. But again, we generally produce this homoscedasticity graph for each and every levels of X, and the distribution should be similar. Okay, something like this. Should be same. That should not be. The distribution should be similar. Okay. Right. This is the very basic setup. So you have things, right? In the basic setup, what we have is that we are trying to produce the line of best fit, and the aim of the line of best fit is to reduce the error, the error between these lines. And sometimes the regression can also go bad. If there is no normality, the data points can also go like this. I hope many of you know about law of diminishing marginal utility, right? Because that defies the linearity assumption. Because reason being, sometimes X increases and Y increase, and later on, whenever X increases, Y decreases. Okay? It is if you know law of diminishing marginal utility, what it basically says is that, okay, as you eat some apple, and your happiness will increase or your satisfaction will increase. But if I ask you to eat more than 3-4 apples, and your satisfaction will come down on apple, right? So you don't want to eat more. Right? So this is a curvilinear type of regression. Okay. And with the normal regression, I'm trying to explain, the DV is a numerical data. Okay, so a lot of information, a lot of writing. Sorry about that, but we have no other choice, right? So it's a linear regression. Imagine the DV is categorical, right? And with two categories, you cannot perform normal linear regression. You can only perform a logistic regression. Yeah. Then if you have more than two categories, it's multinomial regression. Yeah? Okay. Now let's perform regression and interpret it in SPSS. Okay. Let's go to the data file. Here you can see I demarcated certain things so that we don't get into confusion. So you can go to analyze. You can say regression and linear, because we know that it's a linear estimation. As I told you, right, that can be also curve estimation, and for that you need to click this one. Okay, and what we are performing is an ordinary least square model. Okay, so we are just going with that. So if you have partial least square, and then you select this one. As I told you, if the DV is categorical and only has two categories, it's a binary logistic regression. If the DV is categorical and has more than two categories, then it's multinomial logistic regression. Okay. So let's click regression here. So for our understanding, let's expand so that we can see what is DV and other stuff. We're adding DV, and then we have X size. Now we can put all these things into the model. Sorry. Oops. Okay. Okay. So now I'll just remove that. And then statistics, I just want to look at that. And then R-square change is important. And I'll talk briefly about collinear diagnostics, and I'll explain that. And then just continue. And if you want plot, you can also plot this. The plot will give you the residuals. It's kind of residual plot. Okay. And I'm not interested now on that. Maybe let's try. Maybe let's try. Okay, let's not try anything, right? Because it will take more time to explain those stuff. Okay. Then just okay. Here people can ask you like, okay, so what is enter method? Enter method takes all the variable in, but there are many other methods. So there's step-based method. It adds one variable by one variable and sees whether the model is getting better. And to understand these things, we may need one more session, but I'll just go with the default of enter. But there's forward, remove, backward, so which means have full model and then reduce the model, which is backward method. And forward method is like have one variable first and then add other variables and test where it is adding meaningful differences. All right, so now we entered everything to the model, and then we are testing which variable has an impact on the DV. Okay, here you can see the model summary. So this is the first one you should look at, and here the important aspects are R, R square, and adjusted R square. Okay, R is a simple correlation between the independent variable and then the dependent variable, and R square is again the same, but it is squared. But the important thing is that it's adjusted R square. So because this adjusted R square, it takes the sample and approximate that to the population. When you're reporting, and you should normally report the adjusted R square if you're publishing a paper. Okay. And we still do not know whether the model is better or it's fit. And for that, you should look into the ANOVA table. If the significance is there, if it is less than 0.05, it basically says that the model that he produced is robust and it is fit. Okay, we can rely on the model. Now we are looking at the cost. So health cost is the DV, And we are predicting that through age of people and average alcohol consumption and average cigarette consumption and the hours of exercise. Okay. So what should happen if people consume more alcohol and if people consume more cigarette, and that should increase the health cost because they will go to hospital. Yeah. But if in case one person regularly exercises, and that will reduce the health cost of that person on an average. Right? So that is what we also see here. Right? So you need to look at the significance here. Right? And significance is less than 0.05, which means all the independent variables we took for the study do have an impact on the dependent variable. And imagine that if one variable is not having significance, so then we can say that we can just remove that from the model and then fit with the other three variables and then write it. Okay. And also the age, if age increases, the health cost will also increase. Okay. Right. So if you want to put that as an equation, you can write it. So you can say y equals minus 2609 plus 109 age and 47 of alcohol and 138 of cigarette and minus 265 point something of exercise. Okay, so that's the final model result. Okay, maybe I'll just write it and so that you will be able to remember. I'll put it in a different window so that I can write it here. Okay, so let's put the model here. So the cost we are predicting. Okay, and on an average, but people will spend less money. Doesn't make much. They do not spend any money. No, it should be 0, right? But in here the constant is like minus 2609. That's why we don't normally worry about the constant because of that reason. So it is going to be 109 of alcohol. I'll put as A, and then I have plus 47. Sorry, it's age, and then alcohol. I'll say AL, and then you have cigarette. So cigarette is 138 and minus exercise. It's like 265 of exercise. Okay, so if I want to clearly understand the model, so I need to very clear in terms of, I should be very clear about the measurement type. So average hours of exercise. So if I increase the exercise by 1 hour, then I can reduce the cost by $265 or something. Okay, and then if I increase the average cigarette consumption, right, by 1, then I'll increase my health cost by 138. Similarly for alcohol. So which means the cigarette has more impact compared to alcohol. Okay? And also age do have an important, do play a role, but each increase in 1 year of your age increases your cost by $100. Okay, so that is what the model basically says. Okay, and collinearity is a problem, right? So when we add a lot of independent variables, there are chances that these independent variables can correlate together. And for that, if you want to understand whether they are correlated or not, because when you have strong correlation between the independent variables, it can inflate the R-square value. The R-square value is the correlation value, right? So this can get inflated. Hence, what we normally do, we should test this multicollinearity issue. And for that multicollinearity, and if it is, it's not given here, but we normally get a value if it is more than, we normally get a value called as VIF, variation inflation factor. Maybe I did not check it. And if the VIF, the variation inflation factor is more than 5, sorry, and we call that as multicollinear. Okay, it will come for each and every pair of the variables. We can easily find it out. Okay, so that is how you run a regression model and then understand the regression results. Okay, and now I hope I covered everything what I should cover for the day, and also sorry for taking 5 minutes extra of your time. And if you have any questions, I'm ready to answer that. And also, I think there is one question in the chat box. I'll quickly address that one first, and then I'll open myself for the other questions. Okay. So, okay. So there's a question from Kushi Sharma. How can we find out significance value taken while Spearman correlation for hypothesis testing? Okay. Let me show it directly in SPSS. Okay. You can see I can go for correlation. It's like bivariate. Since we know there are many variables here, they are numerical, and I can just go for correlation. So here, I'm going to take Pearson correlation. Just select it. Okay. Now you can see the correlation between cigarette consumption and then alcohol consumption is 0.24. Sorry, 0.42, and it is also significant. So there's a strong, there's a positive, kind of a moderate positive correlation between these two variables. And one thing that we should understand is that the correlation is not causation. Even your regression model is not a causal model. No? We know that how much impact it has. No, one increases, the other increases. It doesn't mean that okay, one causes the other. So that's a major misunderstanding of regression models. Hence, normally researchers will try to establish causality. Causality is established through experiments. Experimentation is the best way to establish causality. Or people who get Nobel prizes for economics, what they do is like they establish causality through statistical test. Okay, and if you want to know more on that, I would recommend you to read econometrics by Jeffrey Woolrich. I think it's introductory econometrics by Jeff Woolrich. I'm putting that in the chat box. Okay. All right. So that's it for the day, and this is my email ID and it's my LinkedIn ID, and you can also find my contact. You can also get the contact from Professor Shamla, and I think she can share my email ID and then my LinkedIn ID. And if you have any questions, feel free to write to me. Now open for questions. Any questions? Yes, Krishna.
So I have two questions related to paired sample t-test. Actually, when we are doing a theoretical study, it is given that if we have a sample size lower than 30, then we'll be applying a t-test. And if we have a sample size of greater than 30, we'll be applying a z-test. But SPSS doesn't differentiate between t-test and z-test. So if I'm performing a test in which I have a sample size of 50, then in my research paper, should I write it as a paired sample t-test or paired sample z-test?
Okay, by any means, it should be only paired sample t-test. Okay, and t-test can also be applied for data points more than 30. No, it's not that it's restricted to less than 30, but there are also many other assumptions for t-test. Okay, hence you don't have to worry much about the results that you are getting out of SPSS. So it should be reported as 2 sample t-test, because you are just trying to compare between two groups and then trying to find a difference. And so I'll just report as it is. And also, don't worry about applying t-test on sample size more than 50. It is completely accepted. Clear?
Thank you, sir. So one more question. Next is that if I'm applying the paired sample t-test, I am measuring the financial knowledge of students before a financial awareness program and after conducting the program. So the test questionnaire should be exactly same, or some questions can be changed in the post training session, or it should be exactly same.
It should be the same, right? Then if the measures are different, then it doesn't correspond to the experiment that you're running, right? Why do the paired sample t-test? The nature itself, it says you test same on 2 different time points, right? Before and after. No, if I collect weight before, then I should also collect weight after. Right? It is not that I should collect weight here and then height here, right? So do the same measure, then it is comparable. If you're doing a different measure, it's not comparable. You cannot compare the means. This comparison of means of the same measure.
Thank you so much, sir.
Thank you very much.
We request the participants to please put up their queries, if any. Okay, so that means the session is absolutely clear to everybody and nobody has any other queries left to be answered.
Like everyone understood. It
Yeah.
looks like everyone understood everything.
Yeah,
So
yes, sir, absolutely, absolutely.
maybe,
Sir.
or I confused them a lot.
Not at all, sir, not at all, sir. So I think we are good to close we can call it the day now. And yeah, okay. So the feedback form is shared. So I would like to formally propose the vote of thanks now. Yeah, okay. So knowledge is like a garden. If not cultivated and nurtured, it cannot be harvested. So the transaction of the knowledge has taken place beautifully in the last 2 days. And now it is up to us to nurture and cultivate it. So first and foremost, I would like to thank God Almighty for the successful completion of this 2-day workshop. I am grateful to the principal of the college, the Bhopal School of Social Sciences, Dr. Father John PJ, for being the pioneer to promote this research culture in our college as well as around us. I am extremely grateful to the conveners of the workshop, Dr. Parminder Kaur, Head of the Department of Economics, BSS, and Professor Laila Simon, Head of Head of the Research Cell, BSS, for their relentless guidance throughout the workshop. My sincere gratitude to our extremely able resource person, Mr. Balachandra K, for steering the workshop so well and sharing his expertise with us. I am sure all of us will agree that the 2 days were extremely helpful for us as researchers. The content delivered by you, sir, had a very high degree of clarity and precision. So, and last but not the least, thank you to all the participants for being with us on board. The feedback link is shared with you all. I think most of you are done with filling the feedback form also. Your certificates will reach you within 15 days on your registered email address. So thank you to all the participants once again, and we definitely would like to see you on board with us for our future endeavors. So thank you one and all. And once again, thank you so much, Mr. Balachanda, for accepting our invitation to become the resource person. It was a delightful experience of 2 days with you. Thanks a lot, sir.
Yeah, it was indeed my pleasure to extend thanks to Professor Dr. Shyamala Hassan. Ma'am, thanks for providing me this opportunity to talk with everybody and share my knowledge or my learnings. I would not say knowledge. And also, it was organized really well, on time, perfect. And I appreciate the organizing team and also all the other dignitaries from your university or the college. And looking forward to associate with you again. And then maybe if people are interested in art programming, and we can connect a workshop on art programming as well.
Absolutely, sir. I think most of the one of the questions of the feedback also says that they can let us know whatever other new topics that they want to learn. So we would be definitely happy to conduct future workshops on the same topic. Yeah, I can just request of the participants to please switch on the cameras. You can just have a virtual photograph here. Just for the record, if you can please switch on the cameras, we can quickly have a photograph.
Hey, super. People are coming in.
Yeah.
Hey, Sagit, Shivam,
Great,
Murli,
great.
Murari, Amal. Yeah. Nice to see you all because I was just talking to the black screen and I never get to see you. And now I'm able to see you all.
So yeah, people are slowly putting on their cameras. Okay. A few more, if at all, can please put on your cameras. We will be delighted to have this photograph, and I'll be sharing this with all of you in your emails. Great. Okay. All right. So thank you so much, one and all. Thank you, sir. And hope to see you all virtually. And probably everything now is normal by God's grace. So probably physically also we'll be inviting you to visit our college. So if you visit India, more than welcome to the college. Please visit us.
Sure, ma'am.
All
Sure,
right. So
definitely.
yeah, thank you so much. So I formally declare the workshop closed. Thank you so much. Have a great
Hi,
day.
everyone. Have a good day.